So this is a method that we're working on for thermal characterization of gallium nitride HEMT technologies. So the idea is that we integrate a test structure in a commercial technology that we can use for thermal characterization. So the idea is that we want to do an electrical method that can be integrated in a packaged device. And we also looked at separating the sensing part from the actual active device, because then we can limit impact of degradation in the active device and also trapping effects. That's a large issue in GaN technologies. And also with electrical methods, we can do this in quite a low-cost setup that most companies have available. So the idea is that we integrate a small MESA resistor that we can use as a sensor. That's a very temperature-dependent component. So we calibrate that for different temperatures, and then we use that as a sensor. And then we have a small heating element placed nearby that we apply a pulse to. And then we get some transient measurements based on the extracted calibration. And then we also extract time constants and weights from these measurements. So for the first experiment, we do for different separation between the sensor and the heater, 3 different separations. And we can see if we reduce the separation, we get a small delay and also increased coupling, so we can capture more time constants. You can also see it's a quite large difference between separations, which is interesting for further studies and calibration of this model. The second experiment is with different dissipated power, and then correspondingly we have different temperatures that we measure. And then we see the conductivity of the semiconductor materials is highly temperature dependent. So we see that thermal resistance increases as the temperature increases in the structure. So that's the second result. And the final result, we looked at 2 different devices placed separately on the chip. So we have one in the corner and one in the center side. And you can see a quite dramatic change to the end of the transient when the heat has diffuses to the edge. So that's something you have to think of when you do designs, that you don't want a device too close to the edge. It gives quite a large impact on the transient. So the conclusion and the work we are using this technique for is to calibrate numerical models, so you can get a very accurate calibration based on these measurements. And we also want to use it for looking at packaging solutions, to get measurements on the die when you have packaged the device. That's something we want to work on. And also we demonstrate here that we can capture quite fast time constants, even though we have a separation between the heat source and the sensor. So you can also see here that we can identify different time constants using this method. So different part of the structure corresponds to different part of the transient. That's the calibration principle. Yeah. And finally, I want to acknowledge the partners. I want to acknowledge Wind Semiconductor for providing their technology and manufacturing these structures. And also the partners in the project, the Gigahertz Chase on Bridge Center, that financed this work. Yeah. Thank you.